Okay, so welcome back, everyone. Quick announcement. By popular demand, I'm shifting my Wednesday office hours to 4 to 5 p.m. starting next week. But again, if that time doesn't work for you, just send me an email and I'm happy to make an appointment at a time that does. So today I want to prove the Riemann mapping theorem, but let me finish up our discussion of the annulus of radius r, which has a very interesting covering map. It's covered by the upper half plane, therefore it has a hyperbolic metric and so on. This is something we were discussing last time. So I use the notation AR to denote the region in the complex plane consisting of the points with little r less than the absolute value of z less than 1. So it's an annular subset of the unit disk. And it turns out that the universal cover here is isomorphic to the upper half plane. So there is a hyperbolic metric, rho of A of r, on this region. And moreover, it turns out that the middle circle of radius r to the 1/2 is a closed geodesic in this region. And in fact, in the hyperbolic metric, in this metric, what the annulus looks like is sort of two trumpet horns glued together. I'm drawing the case where the geodesic is rather short. Maybe that doesn't quite look like my example. Let me modify a little bit. It's in the hyperbolic metric, it's a negatively curved surface, somewhat saddle shaped, and it has infinite volume. And there's one geodesic, gamma, of shortest length. And I'm going to compute the length of this in terms of the number r using the universal covering map, just to complete our calculation from last time. But before I do that, let me mention some other ways of thinking about this annulus. So there's another natural metric on this annulus, which is the metric dz over z. And in this metric, all the circles have length 2 pi, and the height of the annulus is log r. So there's a nice flat metric on this annulus, which makes it look like a Euclidean cylinder. So this is a curvature 0 metric, whereas this is a curvature -1 metric. And in this metric, the height of the annulus is the logarithm of r, and the circumference is 2 pi. So, and there's a conformal isomorphism between these two spaces. So as a Riemann surface, A of r is the same thing as the outside of a tin can. Now, of course, you could also scale this tin can, and that would also be a transformation that's analytic, that preserves angles. You could multiply the metric here by a constant. But there's an invariant of this annulus, which is called its modulus. So the modulus is, by definition, the height over the circumference in this metric, which means that it's the height is log r, and the circumference is 2 pi. Actually, the height is the absolute value of log r, so log 1 over r, since r is less than 1. So this is a good way to think about an annulus. We denote this mod A of r. And there's a nice relationship between the length of this geodesic. This geodesic corresponds in this picture to a circle halfway up the annulus, midway between its two ends. And of course, its Euclidean length is 2 pi, but its hyperbolic length tends to 0 as the height of the cylinder gets larger and larger. And so the theorem that relates the two is conveniently phrased like this: L of gamma, the hyperbolic length of the the core curve of A of R is given by a pi over the modulus of A of R. So if you like to re-express this in terms of R, you can use this expression, and then you'll get 2 pi squared over the logarithm of 1 over R. Okay, so why is this true? Well, let me remind you that we have a map from the upper half plane to this annulus in the complex plane. And this map is given by, let me erase some stuff here.
Oh, there's a raised hand.
Yes.
Richard?
Yeah, I'm wondering for these pictures, how do we see, for example, that the hyperbolic metric makes into this saddle shape?
I'll explain that in a moment. So jumping ahead, it will turn out that there is a circle in the upper half plane of radius 1 and another circle of radius lambda greater than 1, such that the annulus A of R is obtained from this region by gluing the inner and outer boundaries together in the obvious way, by dilation. And our geodesic is covered by the geodesic joining 0 to infinity in the upper half plane. Now, if you remember that the hyperbolic metric is dz over y on the upper half plane, what you can see is that if you were to draw line segments like this, they have the same length in the Euclidean metric, but as they come towards the real axis, this y factor goes to 0, so they blow up exponentially fast in terms of hyperbolic length. So that's how the picture I just described can be justified. You can also write down the hyperbolic metric on A of R from the description of the conformal map I'm about to give. You see this all quite explicitly. Other questions? Okay, so the mapping, which we found last time, f of z is z to the I alpha. We observe that this mapping sends the positive real axis to the unit circle, the negative real axis to the circle of radius r for some value of r. So what is r? Well, the image of -1 is the point r on the inner circle. So r is f of -1. And what's that? It's -1 is e to the pi I. And we raise that to the I alpha. And we get e to the minus pi alpha. So alpha and r are related by this equation. And then we'd like to compute the length of this circle. So the interesting thing about this mapping F, as I've already indicated here, is it is a covering map from the upper half plane to the annulus. And as always for covering spaces, since the fundamental group here is Z, it means there's a group of deck transformations. There's automorphisms of the upper half plane that leave F invariant. And that means there's some lambda bigger than 1, in fact, there's some lambda bigger than 1 such that f of lambda z is f of z. In other words, f is a periodic function, but it's not periodic with respect to addition, it's periodic with respect to multiplication. Multiplication by a positive real number is an automorphism of the upper half plane. This is a fundamental domain for its action. So after I check this, that will explain the explanation I gave of the hyperbolic shape of this annulus. So what's the smallest positive value of lambda, or rather lambda bigger than 1, which satisfies this? Well, you see, what we want to have is that lambda to the I alpha should be equal to 1. So if we write, it's convenient to write lambda as e to the L. And one of the reasons that's useful is that if you go from I to I times lambda, which was what multiplication by lambda does in the upper half plane, then the length in the hyperbolic metric of this segment is L. It's the log of lambda because it's the integral from 1 to lambda of dy over y. So if we write lambda as e to the L, then what we want is that e to the I L alpha should be equal to 1. And the smallest L, which satisfies that, will be the one that makes L alpha equal to 2 pi. So in other words, L is equal to 2 pi over alpha. Okay, so that's how we can compute the length of this closed geodesic. It comes from the periodicity of the covering map F. And then if you want to unwind things, you can observe here that the logarithm of 1 over r is equal to pi times alpha. And so if I've done things right, then I'll get 1 over alpha is pi over log 1 over r. And so this quantity is 2 pi squared over log 1 over r. And that's in agreement with the computation I did here. Okay, so this is an extended example of the computation of a covering map and discussing the hyperbolic geometry of a plane region. Now, by the way, there was a good question after class last time, which was, what good is the hyperbolic metric? And so let me just say a word about that kind of question. The main point of discussing the hyperbolic geometry of plane regions, besides the beautiful fact that every plane region comes with this canonical geometry on it, is that the hyperbolic metric controls the behavior of analytic maps. So if I have a function that takes values in a region, and I want to know how analytic maps behave, then the hyperbolic metric provides a powerful tool for studying that question. So suppose I have some region U in the complex plane, and I have some analytic function. All I know about this function is it's analytic, but I know one more small thing. Let's say I know that the image of this function lies in between the circles of radius 1/2 and 1. So that's an instance of this annulus. And now I also know, for example, that the image of P is the point 3/4 I. This is f of P. And now I draw a small ball in my region. And I'd like to know where the image of this ball lies in the annulus A. For example, is it possible that the image lies all the way over here and hits this point Q? Does f of this ball hit this point Q? Well, the point is that this ball has some diameter in the hyperbolic metric. So I can look at the size of this ball in the hyperbolic metric on my domain U. Now, maybe I don't know my hyperbolic metric on my domain U. That's fine. I can go to a smaller domain where I do know the metric. Just take a disk of some radius S that contains the point I'm interested in. Then I can compute the hyperbolic size of this ball here. And then by the Schwartz lemma, the image of F, of this ball under F, what we call the ball B, the image F of B, which might be some irregular shape, but its diameter in the hyperbolic metric on A is no larger than the original diameter of B in the hyperbolic metric on this disk of radius S. And so if I know what rho of A is explicitly, then I get it bounds on f of B. So that's one reason why one studies the hyperbolic metric is we have very soft information here We just know where the image of F lies as a whole, and we know that F is analytic. And just from those two pieces of information, we get very precise control over where F sends points in one region to another. This is one of many reasons for studying hyperbolic geometry. Another reason is the study of moduli spaces. That is the classification of plane regions or the classification of Riemann surfaces up to conformal isomorphism. So one thing you might wonder is there, for example, a Riemann mapping theorem for annuli? Is there a theorem that says the annulus of radius r is isomorphic to the annulus of radius s? Well, the answer is no, there is no conformal homeomorphism between these two unless r is equal to s. And the reason is any such map must be an isometry for the hyperbolic metric. That's by the Schwarz lemma. And therefore, the length of this chord curve has to be the same as the length of this chord curve. But we've seen that length carries the same information as the modulus of the annulus, or as the number r and s. And so the only way these two annuli can be isomorphic is if they actually have the same modulus. We'll discuss annuli in more detail when we come to the topic of extremal length. This is just a hint of other motivations for studying a hyperbolic metric. Okay, so now I want to come to a big theorem, which I think almost everyone has heard of and perhaps seen a proof of. And I'm going to give the proof fairly rapidly, but I'm going to use the proof to review some basic principles in complex analysis that go into it. So this is the famous Riemann mapping theorem. And it says that among simply connected regions in the plane, there's only one Riemann surface. There's only one conformal isomorphism type, well, except for the plane itself. So the theorem is let U contained in C, U not equal to C, be a simply connected, and of course also connected, open set. Let P be a point in U, then there exists, in fact, a unique conformal isomorphism, in other words, analytic bijection, isomorphism, F from UP to the unit disk 0. That's it. So all simply connected regions are isomorphic to the disk, and just as the icing on the cake, the isomorphism to the disk can be chosen to send any point in the region to the origin, and even arranged so that f prime of p is positive. That the f prime p being positive just takes care of composing with a rotation. Okay. This theorem is quite remarkable for the following reason. It's very easy to write down regions in the plane, like U. A simple case would be a triangle. And as we saw when we studied the Schwarz-Christoffel formula, it's already pretty exotic to find the conformal map from the disk to a triangle. But much worse, you can take the Cauchy snowflake curve, some sort of fractal construction, keep iterating it, get a very complicated region whose boundary is not in the least bit smooth, maybe is even nowhere differentiable. Nevertheless, there is, when you specify this region U, you have then uniquely determined a analytic map from the disk to this region subject to some minor normalization conditions. In particular, there exists an analytic function sending the unit disk to this bizarre looking region. And you might say, how could that possibly be? An analytic map can't send a circle to a fractal. But remember, the mapping F is not even defined initially on the unit circle. It's only defined on the interior here in the unit disk. However, we will later show that whenever the function can be extended continuously to the boundary, it does extend. So in fact, in the case I'm drawing here, the map F is not analytic on the boundary, but it is a homeomorphism to the boundary of this domain mu. In fact, whenever the boundary is a simple closed curve, a Jordan curve in the plane. Okay, so this is the prime example of the flexibility of complex analysis, that regions that satisfy a simple necessary topological condition, namely that they're simply connected like the disk is, are in fact isomorphic to the disk. Now, why do I have to exclude the case where U is C? Well, if U were the complex plane, I would be saying there's a map from the complex plane isomorphically to the unit disk. Actually, we know all the analytic maps from the complex plane to the unit disk. What are they?
Constant.
They're the constants. Every bounded analytic function is constant. So of course, this theorem is false for the complex plane, but it's true for all other regions. And in particular, it's true for regions which might be more exotic than you might imagine at first sight. So of course, it's true for regions that are bounded. But what about a region that looks like this? You take some rays in the complex plane, maybe wobbly ones, that go off to infinity, and you take their complement. This region U is simply connected. Therefore, it is isomorphic to the unit disk. Okay. So let me give the proof of the theorem very fast, say what the outline is, and then we'll go through the details. So for the proof, and this proof is characteristic of many ideas in complex analysis. The idea is that there should be something very special about this map among all maps from U to the unit disk. It should have some extremal property. So a good way to solve a problem is to give a collection of objects, and then within that collection, try to find an extremal object and show that that extremal object solves your problem. It gives you the Riemann map in this case. So we start by defining a collection of mappings. We let F be the set of all analytic maps from UP to delta 0, call them F. And we require not that they're isomorphisms, but we will require that they're one-to-one. And this notation means that, of course, P goes to 0, and then we add the condition that F prime of P is positive. Once the mapping is one-to-one, its derivative at P is not 0, and then you can compose with a rotation to make the derivative positive. That's the first step in the proof, is a definition. Okay, now what do we want to extremize? We want to make the derivative at P as big as possible. The idea being, the more the derivative is expanding, the more of the disk U has to take up. So maybe if we try to make the derivative as big as possible, it will force the map to be injective. So this is the first step of the proof, is just this definition. The second proof step is to show there exists a G in F that maximizes the value of F prime at P. After all, these are positive real numbers. So this requires some sort of compactness argument. Also, we need to know that the maximum is not infinity. And then the third step in the argument is to show that G is surjective. And then that'll imply that it's a bijection because it was injective by assumption. So it is a conformal isomorphism. It does have a positive derivative. And then just the icing on the case is to show that it's unique. Okay. So the first step was easy. It's a definition. It can't go wrong. Let's start looking at the second step. We want to maximize f prime of p. So the first issue is the collection F non-empty? If this is empty, there's no way we're going to be able to solve the maximization problem. So we first have to show that there's at least one map that sends U into the unit disk. Now, if U is a bounded region, that's easy because we can just contract U until its diameter is small and then translate it so it lies in the unit disk. But what about an unbounded region like this? How can we map this region into the unit disk? That's where a little review of complex analysis comes handy. We need to use somewhere the fact that U is simply connected. So we're going to use that at this point. So step one was immediate. For step two, the first thing we prove is that F is non-empty. And to do this, we observe that if U is simply connected, in other words, if its fundamental group is trivial, this implies there exists a function, which I'll call log, mapping U to the complex plane. And why do I call it log? Well, first, it's continuous, it's analytic, and it has the property that e to the log of z is equal to z. To put it differently, there is a single valued branch of the logarithm defined on any region U, provided one thing happens. It's dangerous to take the logarithm of 0. This should be minus infinity, so we can't be analytic there. So let's suppose that U is simply connected and 0 is not in U. Then there is a single valued branch of the logarithm defined on U. Okay, now why is this true? This is a fact we use all the time. It's because we can define log as follows. We simply say log of z is the integral, it's log of z0 plus the integral from z0 to z of d zeta over zeta, where what this integral means is that we're in our domain U and we choose any path we like that goes from z0 to z. So actually we integrate along a path gamma this function d zeta over zeta. Okay, now why should this work? Well, it should work because the derivative of log z is 1 over z. So we're integrating something whose derivative is log, and this log z naught at the beginning assures us that the integral is equal to log at some point, and so by continuity, it has to be equal to a branch of the logarithm everywhere. The problem is what I've written down here well defined? But the answer is yes, and it's because if we choose a different path, delta, that goes from z naught to z, then because U is simply connected, the integral around this closed loop, where you first do gamma and then you do delta backwards, the integral of this quantity around this closed loop is 0. Of course, this function d zeta over zeta, it has a pole when zeta is equal to 0, but 0 is not in our domain. And this loop can be contracted without leaving the domain because pi 1 of U is equal to 0. So therefore, these two integrals agree and this function is well defined. Okay, so that's the first step in the proof, is to observe that there's a logarithm on any simply connected region. And we're going to use this fact more than once. Now, what good is the logarithm? The logarithm is really a proxy for a lot of other functions. You see, once you have a well-defined branch of the logarithm, we can also define, for example, z to the alpha, mapping U to c. by just setting this equal to e to the alpha times the logarithm of z, where the logarithm is what we constructed here. So there's a globally defined single valued branch of z to the alpha, and in particular, we can also define the square root of z, mapping u to c. And so for any region u, provided it does not contain the origin, you can take the square root of z, apply it to u, and map it to a new region in the plane. Now, one thing we know about the square root of z when we've done this is if we go backwards by z squared, it inverts the square root. So this mapping is 1 to 1. But that means that v intersect minus v is empty. If you have a region that's, if the squaring map is 1 to 1, it can't contain both p and minus p, because then those 2 points would map to the same point. So the image of any region under the square root consists of 2 regions, one of which is the negative of another. Let's just think about an unbounded example. If we were to take u to be the first quadrant, then when we take the square root of u, we would get an even narrower or octant of the plane. This would be our region V, and this would be disjoint from the other possible values of the square root, which are down here. Now, the beauty of the fact that the image is disjoint from its negative is that we can find a point P, which is a definite distance away from the boundary of V. And the reason that's good is if we have a point P that's not in V, then we can apply to the Mobius transformation that sends P to infinity. And as long as P is not in the closure of V, V will be sent to a bounded domain. So if we further apply the mapping 1 over z minus p to this region V, this is sent to some region, let me call it W, and W contained in C is bounded. Okay, so how does this show that F is non-empty? It shows that we can apply a series of conformal isomorphisms to finally map U isomorphically to a bounded domain, and then we can scale that and put it inside the unit disk. Okay, so what's the procedure? First, we translate U. So U does not contain 0. Then we replace U with the square root of U. So then we say U, replace it with its image under a single valued square root. And then we invert, that is, we apply the map 1 over z minus p to get to something that's bounded. And then we scale and translate to get inside, to get something that fits inside the unit disk. Okay, so the first step just uses the simple connectivity to construct square roots. And that is somehow the key idea in modern proofs of the Riemann mapping theorem, is that simply connected domains admit square roots. So the first step is to say that this is not empty because of the existence of the square root. Okay. Long-winded way to prove that the set that was defined in step 1 is not vacuous. Now the second thing is, why should there exist an element here that maximizes f prime of p? Why, by the way, is f prime of p even bounded above? So the second thing we'll show is that f prime of p is less than or equal to a constant. In fact, it's less than or equal to 1 over the distance from P to the boundary of U for all F and F. So it is in fact bounded above. Now why is this? Well, here's our domain U. We have our point P. One thing we know is that NEF is defined on the ball of radius r around P, where r is the distance to the boundary, the minimum distance to the boundary. So we have a map that sends the disk of radius r to the disk of radius 1, sending the center to the center. Now, if this disk was also of radius 1, the Schwarz lemma would imply that f prime is less than or equal to 1. But because this disk is smaller, it's possible to expand it by a factor of 1 over r, but that's the worst you can do. So this is by the Schwarz lemma. So that's the second main ingredient in the proof is the Schwarz lemma. Okay, now that's good. So we're trying to optimize a function f prime that's bounded at least. How do we know that the maximum exists? Well, the usual way to try to prove the maximum of a function exists on some set is to show that the function of interest is continuous and the set is compact. Okay, so what topology should we put on F if we want to apply that argument? So this now is just a definition. We give F the topology of uniform convergence on compact sets. In other words, we say Fn tends to G if for any compact set K contained in U, the sup over K of the absolute value of Fn of Z minus G of Z tends to 0. Now, what would be nice would be if F were actually compact in this topology, and that's almost the case. So let me review some properties about uniform convergence on compact sets. So the first property is that if the Fn are analytic and they converge uniformly to an a priori just a continuous function G, in fact, G is analytic. One way to prove this is to use Morera's characterization of analytic functions. Analytic functions are exactly the ones with the property that if you take a closed loop bounding a disk inside your region, then the integral over gamma of Fn should be equal to 0. That characterizes analytic functions, that they satisfy Cauchy's integral formula, Cauchy's integral theorem, I should say. But the integral is a continuous function of Fn in the uniform topology. It doesn't use the derivative of f at all. And so this converges to the integral of gamma of G. So G satisfies Morera's theorem, and therefore it's still analytic. So uniform limits preserve analyticity, and even better, it also implies that Fn prime of Z tends to G prime of Z. Again, pointwise, but also uniformly on compact sets. And similarly for all further derivatives. So that's a pretty good step towards compactness. We have a topology, and if we can take limits in this topology, the functions remain analytic. What else? Well, what we'd also like to have is some kind of compactness. How can we ever get uniform convergence out of a sequence of functions? Well, for this, we use the fact that these functions are all bounded. They all map into the unit disk. And it's a very general principle that a bound on F gives a bound on F prime, which in turn gives a bound on F double prime, and so on. Once a function is bounded, all of its derivatives are bounded. So how do we prove that? So I need to make a little room here, but this will be D. So we've introduced this nice topology. It preserves analyticity. And now some compactness, we'll call this pre-compactness. Provided F is in our family F, we have that the absolute value of F prime of Z is less than or equal to, and again, we can give a very explicit bound here. It's 1 over the distance from Z to the boundary of U for all Z in U and for all F in our family. So we have uniform control over the size of the derivative of F. Where does this come from? Here we can use Cauchy's integral formula. Again, we'll work on the disk of radius r around a point where r is the distance to the boundary. There's a formula for F prime of Z. F prime of Z is 1 over 2 pi I times the integral over the circle of radius r of F of Z, or F of zeta, d zeta, over Z minus zeta squared. That's obtained by just taking the usual Cauchy integral formula and differentiating once with respect to Z. So how can we bound this? We'll notice that the length of this circle is at most is 2 pi r. And this quantity on the boundary, you see we're at this point Z, zeta is moving over the circle of radius r. So this quantity on the bottom is equal to r squared in absolute value. So this is less than or equal to 1 over 2 pi times the length of the region on which we're integrating, 2 pi r, times an upper bound on which we're integrating. F is bounded by 1 since it maps into the unit disk, and the denominator is bounded by below by r squared. And so we cancel out the 2 pi's, we cancel out 1r, and we get that F prime is less than or equal to 1 over r. That is, F prime is bounded by the distance to the boundary. Okay, so that is a typical way of leveraging boundedness to get control over higher order derivatives. And what can we conclude from this condition? Well, there's a basic theorem in real analysis called the Arzela-Scully theorem. It says if you have a family of functions and the functions are bounded and their modulus of continuity is bounded, in particular if their derivatives are uniformly bounded, then they have a uniformly convergent subsequence. Now suppose we have a compact set in our region U, then the distance from K to the boundary of U is bounded below. So on that compact set, the derivative of F is bounded above, so its oscillations are controlled. On the other hand, the function itself is also bounded because it takes values in the unit disk. And so by applying the Arzela-Scully theorem, we find that any sequence in F has a convergent subsequence. Say Fn tends to G. Now we haven't yet proved that G is in F, but we've come pretty close. We've proved that G is analytic, and also we've proved that G prime of P is the limit of Fn prime of P. So the program for completing step 2 is now very simple. We know that the sup of Fn prime at P is bounded above, so we can choose a sequence, Fn, that converges to the sup. We then choose a subsequence such that that Fn limits on an analytic function. This analytic function then has G prime equal to the maximum of F prime at P over all F in our family. So it does indeed maximize this value. And it's analytic. It still maps U into the disk. It still sends P to 0. But is it one-to-one? If we have a sequence of analytic functions that are one-to-one, does the limit have to be injective? Unfortunately, the fact that a function is one-to-one is not preserved in the limit always. If you take Fn of z is z over n, this is injective on the whole complex plane, but it converges uniformly on convex sets to the function f of z equals 0, which is of course not injective. But that's the only counterexample. As long as this function g is not the constant function, it remains injective. And of course, it's not the constant function because g prime of p is non-zero. It realizes the maximum of this quantity over the whole family f. So we know that this limit is not constant, and then we claim that g is one-to-one. Okay, so this final claim is something that is sort of intuitively obvious. To make it formally correct, though, it's good to appeal to the argument principle. So again, this reviews one more basic concept in complex analysis. So for this last step, maybe this is E, G is one-to-one. We're going to use the argument principle. And let me remind you what this says. So first, I should say a word about why it's obvious that G is one-to-one. See, suppose you have your region U, and you have a mapping G, and this mapping is not one-to-one. So it might do something like this. It might be that the image, G of U, overlaps itself. So that there's 2 points here, P and Q, and they get mapped to the same point in the target. Okay, now, suppose you have a sequence of mappings that approximate G. Well, it's intuitively obvious that the image still comes around and overlaps itself. You can't make that overlapping of these two sheets of the image disappear by a small perturbation. And in fact, that's a general principle about analytic functions. When their graphs cross, they cross transversely with positive intersection number. You can't get rid of that intersection by a small perturbation. Anyway, that intuition is made precise by the argument principle. So let me say what the argument principle says. We can, again, consider the case just of a function that's defined, let's say, near some point Q on a ball of radius r. Let's call this B. We have a function f into the complex plane. And the argument principle says that if f restricted to the boundary of B has no zeros, then n of f, which is the number of zeros of f in B, is given by an integral. It's given by 1 over 2 pi I, the integral over the boundary of B, of f prime of z dz over f of z. And this integral is doing something very simple. You look at the boundary of B, here's 0 in the complex plane, and the image of the boundary might go something like this. What this integral does is it calculates how many times the image of the boundary winds around 0. And then it says that if the image winds, say, 3 times around 0, then the function f has 3 zeros inside the unit disk. Those zeros are, of course, counted with multiplicities. Okay, so that's the argument principle. It's easily proved by applying the residue theorem. at any zero of f, you get a residue that's equal to the multiplicity of the zero of f, which is always a non-negative number. One thing that's quite remarkable about the argument principle is that the number that we get again at the end is an integer, indeed a non-negative integer, even though we've done this complicated integral. One thing that this proves is the following. Suppose f has no zeros, and now suppose fn converges to f uniformly on B. Well, then eventually fn doesn't have any zeros on the boundary either. And so these integrals, which are the integrals for fn, converge to the integral for f. But these integrals are taking values in the integers. So if you have a convergent sequence of integers, it must be constant eventually. And what that means that if fn tends to f uniformly, then the number of zeros of fn is equal to the number of zeros of f for all n sufficiently large. That's what the argument principle is for. It guarantees stability of the number of zeros. Okay, so with that in mind, we can now complete the proof that G is 1 to 1. So if G of Z1 were to be equal to Z2, where Z1 is not equal to Z2 in our region U, so we have two different points, Z1 and Z2, that map to the same point, then we choose a small ball around B that excludes the point Z2, and such that G of Z1, Z is not equal to Z2 on the boundary of this ball. So then what we find, let me call this N sub B. What we find is that N sub B of G of Z minus G of Z2 is greater than 0. The number of times that G of Z assumes the value Z2, in other words, the number of zeros of this function, is positive because there is a 0 in particular at Z1, and that's inside of B. But now this means that the number of zeros of Fn of Z minus Fn of Z2 is also greater than 0 for all n sufficiently large. Remember, the Fn's are in our family F. They're supposed to be 1 to 1. But when this is positive, it means that there is some point, maybe not Z1 anymore, but a new point, Z1 prime in B, such that Fn of Z1 prime equals Fn of Z2. And that contradicts the fact that Fn is 1 to 1. Okay, so the argument principle ensures that the limit is injective, and that justifies step 2. Okay, so we're almost done. And I should say that once you've absorbed these kind of basic principles of complex analysis, step 2 is very fast. That's the easy part. The tricky part is, and this really is based on sort of a trick, is to prove that this extremal function must be surjective onto the unit disk. And the way one proves that is by contradiction. You say, if this function doesn't use the whole unit disk, if its image is not the whole unit disk, then I can construct a new function in F whose derivative is bigger at P. So we didn't maximize the derivative. So that's step 3. Any questions before we proceed to step 3? I should say I've sketched all this in the notes as well. I know it's hard to follow sometimes on the Blackboard with the frequent erasures. And of course, all the lectures are taped in case you'd like to review, even at 4 times usual speed. Okay, so step 3. G is surjective. So we suppose not. So V, which is the image of U, is contained in the unit disk, but it's not equal to it. So we started with our domain U, we mapped it by G into the unit disk, and the point P went to 0, and then we got some region phi, but we didn't use the whole unit disk. I say, well, that was a bad choice. The reason I know that's a bad choice is the following. Well, let me first apply an automorphism of the disk, that is a Mobius transformation, to move V so it doesn't include the origin. You see, if this is not equal to the disk, then we can choose a point Q that's in the disk but not in V. So we pick some point Q here. And now we know the automorphisms of the disk act transitively, so we can certainly move Q to the origin. So we just make a change of coordinates now so that Q is over here. And f of P remains marked, it's inside of A and B. Sorry, we move Q to the origin. So in other words, we arrange that the origin is not in A and B. We did that trick already once. When did we do it? We did it when we constructed a square root on U, and we're going to construct a square root again. So now what we do is we consider the map Z goes to Z squared on the unit disk. This map is 2 to 1, but it's only branched over the origin. The preimage of A and B consists of two pieces. There's a piece W up here, and there's a piece minus W down here, and they're disjoint because the origin is not in W, and because this region is simply connected. And indeed, if we call this the squaring map S, because this region is simply connected and doesn't contain 0, we can find a single valued branch of S inverse, i.e. the square root of Z, on the region A of V. And the marked point, which started out being P, went to 0, then it went over here. There's still a marked point here in W. And now, to fix everything up, we apply an automorphism of the disk one more time to move this marked point back to the origin. So we're going to arrange that B of W looks like this, and this marked point goes back to the origin, and we even apply a rotation to ensure that when we go all the way through this whole composition, we get a new mapping, which I'll call H. So H is this composition, B composed with S inverse, composed with A, composed with G, that this mapping sends P to 0, and that its derivative at 0 if P is greater than 0. So H of P is positive. Okay, now everything in sight is univalent. So this function H is 1 to 1, and of course it's analytic and it's normalized. It sends our region to the disk. Our claim is that H prime of P is bigger than G prime of P. That G prime did not maximize the derivative. So that will complete the proof. We need to show that H prime of P is strictly bigger than G prime of P. Now, why is that? Well, let's try to take H and recover G. So if we do H, how do we get back to G? We apply B inverse, then we apply S, and then we apply A inverse. So H is the composition of this mapping. Let's see, at the end I apply A inverse. So A inverse composed with S, composed with B, composed with G. Now what is this mapping? This is very simple. You do a Mobius transformation, you square, and you do another Mobius transformation. And let's look where it sends 0. This mapping sends 0 to here, and then to here. Sorry, I think I did one too many sorry, that's right. So it sends 0 to this base point, to this base point, and then to 0 again. So this is a map of the disk to itself. Let me call it F. This is a map from the disk to itself, and it sends 0 to 0. But it's not an isomorphism, because in the middle we have this squaring map. This map is 2 to 1. And so by the Schwartz lemma, f prime of 0 is in absolute value strictly less than 1. But what's h prime of 0? H prime of 0 by the chain rule is f prime of 0 times g prime of 0. And since this is strictly less than 1, h prime of 0 is strictly bigger than g prime of 0. Okay, so if the map weren't surjective, we can apply a square root argument to get a map with an even larger derivative. And again, the key point is the Schwartz lemma, although it's the Schwartz lemma in a very simple case. This mapping is so explicit, you don't really need the Schwartz lemma to prove that it's a contraction. Okay, so that's the proof that G is surjective. And that's really the end of the proof of the Riemann mapping theorem. It would be nice to have uniqueness, but that's easy, because if you have two maps to the unit disk that are normalized in the same way, so if we have a G1 and we have a G2, they're isomorphisms to the unit disk, sending P to 0, then their difference, if we go back by one and over by the other, their difference would be an automorphism of the disk with the property that A of 0 is 0 and A prime of 0 is 1, or at least is positive. But then that implies, since A is a rotation, that A prime of 0 is 1, and in fact that A is like the identity. Okay, therefore the Riemann mapping is indeed unique. Great. So this concludes the proof of the Riemann mapping theorem in detail, and I hope it's been useful to just touch on some of the more elementary aspects of complex analysis, like the argument principle, to see how they enter the proof. Okay. Now, I'd like to make a remark, just as like a sort of a sorbet, a sort of palate cleanser before we do more complex analysis, which is that at the end of the day, we've used analytic methods to prove a theorem in topology. Because what we started with was not the assumption that our domain U was homeomorphic to the unit disk. What we started with was the assumption that our domain U is simply connected. And the fundamental group is a homotopy invariant. And in fact, for regions in the plane, or for surfaces, the assumption that it's simply connected is the same as the assumption that it's contractible. So what we proved is the following topological corollary. Let U contained in C be a contractible open set. Then U is homeomorphic to the unit disk. Of course, we proved much more. We proved that it's analytically isomorphic to the unit disk, at least as long as it's not the complex plane itself. Okay, now you might say, well, yes, but isn't that pretty obvious? So if you have a domain, to say it's contractible basically means it doesn't have any holes in it. And if it doesn't have any holes in it, it's sort of obviously a disk. Just straighten out the boundary. But that intuitive argument, which I think is appealing, actually requires quite a bit of topological work to justify. So in fact, the Riemann mapping theorem is one of the most efficient proofs of this purely topological theorem. That's the first comment. The second comment is that You might say, but this theorem is not at all surprising. Well, I think it should, just to give you a little bit of pause, I'm going to mention that this theorem is false in dimension 3. So on the other hand, there exists a contractible open set U contained in R3 such that U is not homeomorphic to the 3-ball. And in fact, this example was discovered by Whitehead when he was trying to prove the Poincare conjecture, namely that any simply connected closed 3-manifold is homeomorphic to the 3-sphere. And his proof was, well, you take out a ball from your manifold, and what's left over you can prove to be contractible, and therefore your manifold is just the union of 2 balls, and therefore it's the sphere. But unfortunately, there exist wild contractible sets. So let me just, as a sort of cultural aside, give you a glimpse of what this counterexample is that Whitehead presented. It's a little bit simpler to put it in the 3-dimensional sphere rather than the 3-dimensional ball. But not too bad. So let me say how U is constructed. So the first thing is to think about a solid torus, T1, contained in the 3-sphere. Now, it's a beautiful fact that if you take a solid torus out of the 3-dimensional sphere, what's left over is also a solid torus. It's a solid torus that goes up through this hole, goes past infinity, and comes back on the other side. So the 3-sphere is actually the union of 2 solid tori. And in particular, the complement of this 3 torus in the 3-sphere has fundamental group Z. So pi1, so our first approximation to U is that it's something like S3 minus T1. But the problem is pi1 of S3 minus T1 is isomorphic to Z. So what we do is, and this is Whitehead's great idea, is inside of our first torus T1, we take a second torus T2. It's not going to be very thick, so I'm going to draw it as a straight line. And this second torus goes around inside of T2, but it doesn't, the core curve of this torus is trivial in the fundamental group of T1. It doesn't have any winding number inside of T1. And so the fundamental group of the complement of T1 is generated by this loop here. But this loop has 0 linking number with this torus. And therefore, this loop is trivial in the fundamental group of the complement of T2. So in other words, the map from the fundamental group of S3 minus T1 into the fundamental group of S3 minus T2, both of these groups are Z, but this map sends the generator 1 to 0. And so in brief, Whitehead's example is obtained in the following way. You construct a nested sequence of solid tori such that T3 wraps around inside of T2 the same way T2 wrapped around inside of T1. And then you let U be the union of UI, where UI is S3 minus Ti. And it's easy to prove that pi2 of all of these UIs are equal to 0. So pi2 of U is equal to 0. And pi1 of U is the limit, direct limit of pi1 of the UI. And each of these is a Z mapping into the next. but each of these maps is the 0 map. And so pi1 is also equal to 0. And then it's a basic fact in homotopy theory that if you have a 3-dimensional space and its first two homotopy groups vanish, well, its third homotopy group also vanishes trivially, then it's contractible. All the homotopy groups vanish, and therefore it's a contractible space. So this implies U is contractible. It's the complement of some rather wild fractal-looking set in the 3-sphere. And then finally, you can prove that this loop does not bound a disk inside of U. And that's a characteristic property of a ball. In a ball, any loop, any simple loop bounds a disk. And since that's violated, U is not homeomorphic to the 3-ball. Okay, so just a hint of the fact that we've actually proved a theorem that at least is non-trivial in higher dimensions. Okay, so many discussions of the Riemann mapping theorem stop here, but I think there's a very important assertion that, that needs to be added, which is what is the boundary behavior of the Riemann mapping? Somehow mappings on open sets, even when they're homeomorphisms, they don't feel nearly as controlled as mappings on compact sets. Mappings on compact sets are equally continuous. So here's a sample theorem about the behavior of the Riemann mapping. So let U be a Jordan domain in C. That is, the boundary of U is a simple closed curve, which just means a topological copy of the unit circle. No assumption of differentiability. Then the Riemann map from U to the disk extends to a homeomorphism from U bar to the closed disk. In particular, if we consider the mapping F inverse, this gives a natural parameterization of the boundary of U by points on the circle. Okay, so the Riemann map extends to the boundary when it can. Now you might wonder, is it maybe always true that the Riemann mapping or its inverse extends to the boundary? And unfortunately, this is not quite true. But the failure happens only in rather pathological circumstances. So let me just finish by giving you an example of a really exotic domain which admits a Riemann mapping, but where the Riemann mapping is not so well behaved. And by the way, although in the proof I constructed the Riemann mapping going from U to delta, in applications we often use the isomorphism going the other way from delta to U. So let me just think in those terms for this example. Suppose I consider the Riemann map to U, where U is this simply connected domain. I take a square, and then I start deleting needles that go 90% of the way off the square, or across the square in opposite directions. Okay, is the picture clear? And now here's the unit disk, and by our theorem, there is a homeomorphism from the unit disk to the interior of this region. But we could ask, does it extend to even a continuous map from the circle to the boundary? Well, if it did, there would be some point on the circle that maps to the bottom of the rectangle. And then, if we drew an a radius that terminates at that point P, we would get a path that lies in the interior of U and converges to the point P. So what would the image of this path look like? Well, this path has to zigzag back and forth. So no matter how the map is chosen, this path can't possibly converge to the point F of P. The point F of P is said to be inaccessible from within U. There is no continuous arc in U that converges to this point P. And therefore, the Riemann mapping F to this region cannot extend continuously to the boundary. But of course, the hypothesis that the boundary is a Jordan curve rules out that kind of behavior and gives us this stronger conclusion. Okay, so we'll discuss the boundary behavior next time. And as usual, I'll hang out after the recording stops.